All right, in this video, I want to discuss like a little weird experimental thing that I came up with for potentially simplifying VR, but it's probably not worth it. It's probably too much trouble. So hopefully you've seen my examples, and you saw that the most time-consuming part of the method is really having to check multiple VRs, rather than really like check step 2 is easy, step 1 is easy, even having to come up with VRG plus 2 is easy. The real difficult part, or like the really time consuming part, is checking multiple VRs. So I kind of devised a method for you to avoid having to do this exactly. Not quite, like obviously you still have to check multiple VRs, but like all the risk handling, backtracking, I kind of like wanted to devise a method that avoids that. Again, I don't think it's worth it. The only use case maybe will be something like you have multiple VRs of the same length, and there's just so many that like trying to backtrack is a huge issue. But I don't know, like I gave you multiple examples of VR, and I don't think for any of them doing this is worth it. So, but I still wanted to show you because like it's fun and there's some cool math involved, and it's a cool idea. Just learn all the ideas. This video is just for theory maxers. I'm not even going to explain the method entirely. Like, I'm just going to leave some details up to the reader, to the listener, the reviewer, I guess. I'm assuming you're actually looking at this, right? You're not just listening to my voice. Right, so the main problem is how do you predict step 2? And what I mean is particular, right? I mean, like, how do you predict the Tsui? And this is hard. This is actually hard. If you're trying to just write S4 as a semi-direct product between V and S3, the rules are kind of complicated, and it's not easier than just tracking an edge throughout. So that doesn't quite work. I mean, it works, but like it's not good enough for me. So what I figured out is that, let's say you have some example skeleton on the like. If the word stop disconnecting, that would be great. Now let's just say yes, something like this. No, like let's also put something at the end. I don't know. And let's just say you have a VR, something like this. Then, okay, how do you predict the Tsui? So what I figured is that so let's consider the insertion of a single E move at a time. Okay. Obviously, we can't insert a single E move. You're gonna have to insert at least 2. But let's just do that. So what happens when you insert an E move somewhere in the skeleton? Well, it's inserting an E move in the skeleton is the same thing as adding at the end, well, all the moves preceding this prime conjugate E. Same thing as this. And okay, this is basically the same as doing a fourth cycle. And alright, so the first problem, doing a fourth cycle, like just multiplying a fourth cycle is difficult. Like, how on earth are you gonna do that? If you try, like, you're gonna have to turn the cube maybe. So here comes one of my first ideas. S4 is isomorphic to the group of cube rotations. Which is, yeah, pretty interesting fact. So, yeah, just to show you how this isomorphism works, let's draw a cube. I'm bad at drawing, but hopefully this is good enough. And then you consider all the 4 diagonals. So I'm going to color them. Hopefully it makes it a bit less cluttered. I don't know, at this color. It's still cluttered. Okay, but you know there are 4 diagonals. And basically, if you numbered these diagonals, then a cube rotation, all the 24 cube rotations are in one-to-one correspondence to all the permutations of the diagonals, basically. I guess the way I phrase it didn't need to number through diagonals, but whatever. I said it. Like, you can't undo me. So yeah. So what you can do is you can take if you have like edges in the E-slice, you can consider the corners around top of them, and you can try to put the cube in this configuration. So I guess just a quick justification of this. Just as an exercise, generate a two-swap of two adjacent diagonals. Yeah, the fact that you can do it here means you can do it here by symmetry, so just do any one of them. Opposite doesn't quite work, for the argument, but yeah. And you just use the fact that adjacent transposition generate the entire thing. You actually need the fourth one. You just need three, because yeah. Also, you might notice that there are 24 of each, so that's also like a good thing to check. Notice how I'm only considering rotations. I'm not considering flipping symmetries. So physical rotations that you can do in 3D in physical space. Determinant one. That's the thing I'm looking for. Right. So one thing that's really nice about this isomorphism is that 4 cycles correspond to phase rotations. Or I guess rotations around an axis. Let's put it like this. By 90 degrees. So in particular, they correspond to x, x prime, y, y prime, z, z prime. And remember, the previous video, we actually computed how many 4 cycles are. There are 6. So yeah, that coincides. Yeah, that's what we're going to use. So if we are able to consider the final state and translate it to a rotation, then we can, if we can determine what rotations correspond to a spot, like to an E moving cylinder spot with skeleton, then we can just apply the rotation on your cube there, right? And then if you do this for all the slices, and you have to do this from left to right, because basically you want to insert this slice first and then this slice. I guess I can explain it better. Basically, let's say we want to insert E prime and then E, for example. I guess you wouldn't want to do that for the examples I have. So let's do it this way instead. This is the same thing as adding, so L2U, F2U, R2, B2 prime, conjugated with E, and then add, I guess let's make this blue. And then F2, U, R2, B2. Notice how inserting this E doesn't really modify anything in here, which is why we want to insert this one first. Yeah. So if you're able to determine what these rotations correspond to, then we can just apply on the cube. And then you just need to turn the final cube into your final 3-2E. And the only thing you need to do is determine if centers are solved or not. But that's easy. You can do that. Come on. You're not dumb, are you? Why are you watching this video? So now the thing you need to do is how do you figure out what rotations correspond to E or E prime? And so the way you do this is well, okay, you could just kind of backtrack and like do rotations on cube, but that's bad. That's actually like really slow. Like doing the cube rotation corresponding to like the B2 swap is actually much slower than just doing B2. So that's not flying. That's not gonna fly here. So instead, what we can do is we look mod V first of all. Well, not really. So here's actually what we do. Let me copy this actually. Just to have a skeleton that I can. All right. I guess it's going here. So what we do is if you're here, we consider this sequence, which is I guess that let's pick another example actually. Let's just pick this one. So let's say we want to determine the effect of insertion of, say, an E move there. Okay. So now we consider this sequence, okay, which is ignoring U moves, because U moves don't affect the E slice. This is L2, F2, R2, B2. What we do now is we determine whether it's an I or D sequence. Most importantly, we determine if we like what moves to add at the end in order to make this into an I or D sequence. So let's do our algorithm. We got this, and then here we actually we don't get anything. So far our previous algorithm just tells you that this is not an I or D sequence. But now basically what we want to do is basically append F2 F2, and basically you get the residual is an F2. So this is an I sequence and this is a D sequence. So basically you get that this is a D sequence plus F2, or I guess times F2. It's weird, but whatever. And this is useful because basically this if let's say your cube is in WCI orientation, so one in top, green in front, with a standard color scheme. Hopefully you did the exercise of determining what cube rotation corresponds to a swap, and in particular the one corresponding to I guess this diagonal here, the ones in the front. This of course puts the green on top, right? So basically what happens is you're putting the green on top. So remember now we need to consider this thing. So we need to consider L2, F2, R2, B2, F2, F2. I'm gonna write it like this, prime. And then we want to insert an E move. We want to determine what this is, right? And so basically what you're doing is you're putting green on top, and then if you just follow these moves around, right? Remember this sequence lies in D4. This part here lies in D4. And when a sequence lies in D4, its cube rotation, well, it lies in D4. What do I mean? It means that it preserves the top and bottom axis. Okay, I don't think that's hard to prove. You can, that's very easy to show actually. Because it preserves the top and bottom axis, in particular, we know that in this case it actually flips the cube around. So we know that by the end of this sequence we have the blue on the top, right? So we have some rotate. So basically, our equivalent cube rotation is going to be something that puts. So we're going to have something that puts blue on top. Then we're going to do an E move. Well, an E move corresponds to a Y prime rotation, just because E moves are broken. And then the same thing prime, which means we're doing a counterclockwise rotation around the blue side, which is a Z rotation. And that's how you determine the fourth cycle. So basically, you find your VR, you pick the VR that you're trying to solve, and then you just determine that. And also there are shortcuts because, for example, this is an I sequence. So an E prime here corresponds to a Y prime. And now if we try to do this one, notice how here there's R2 and L2. So we get R2, L2, which is D sequence, and then we have this. So we don't really have to do extra work. We know that E prime corresponds to Y. And in particular, it turns out that you're going to have to do this calculation originally only 3 times at most. Because S4, basically, the quotient of S4 by D4, like where you are depends on mod V, but also it depends on like the non-parity component. So yeah, basically it turns out to just depend on the signs and whatever. I've tried to prove that. Try to understand what I'm saying and proving that as an exercise. Right. So the last thing you're gonna have to do is actually figure out how do we find the step 2 on paper? Because yeah, how to do step 2 on paper? That's the last thing we need to do. So we have, let's say we have some, I'm gonna be making something up. U R2 U wide prime F2 R2 U wide R2 U. Now, let me actually also do the conversion into science, by the way. So like this would be minus plus, but we picked this one because there's U wides. Okay. So here's a nice result. Let's say you actually, okay, let's just first do an example of the of a skeleton where you didn't actually, like something already in VR where you didn't actually have to insert wide moves. So U R2 U2 F2 R2 U B2 U2 R2, something like this. Okay. Let's do the conversion into science. Okay, that's actually quite boring. So here's a nice result. What happens when you insert here only depends on the sum of the numbers succeeding this. This is because, again, inserting here is the same thing as inserting, in this case, it'll be R2, E2, R2. So conjugation by the inverse of these moves, right? But the action, the conjugation action of S4 on E2, so the conjugation action factors through S4 mod V. And actually, not only that, it factors through like S4 mod D8. D4, I called it. That's not really a group, but yeah, R2 like R2 F2 R2 commutes with E2. That's the easy way to put it as, which actually implies that yes, we can just care about the sum of the signs. You can use this sometimes to determine whether whether a step 2 is plus 0 just by looking at the skeleton and notice that yeah, everything is possible basically. It's rare that you can do this because you need enough U2s or like an E in the middle of everything. But yeah, sometimes you can do this. So I guess here, like R2 to R2, that's F because that's minus. Here we have, I guess it's the same. Let me actually change up the example a little bit. Let me just do that. Okay. And in this case, this is G, because there's minus, that's G. This is red. So I guess inserting U2 here, that'll be G and that'll be F. If you have a something wide insert in the middle, you're gonna have to be careful that the things that you pick basically have to be changed to their opposites. So plus is good, minus. And then you can use, I guess here I didn't insert any U2 moves, but I don't know. Maybe try and look for, where's the +1 because you try to look for +1 because that's like centers are unsolved. Then okay, you can look here, that's G. You can look here, that's R. Sorry, that's F. Here, that's G again. Here, that's R. So actually, everything is possible. I think that's all that I wanted to say. This method is interesting. I don't think it's useful. Like, it's just some kind of experimental stuff I thought of, but like I thought about it. I don't really think it's useful. I just think just checking the VR stuff with your cube, backtrack and stuff. I think that's the optimal. Like the only thing that can convince me is if you get some sort of situation where you get like 10 VRs of +2 because you have like I don't know, you have a 3 QT things, but the +0s and +1 just don't work out, and you have to track 10 +2s, and I don't even know if the 10 +2s are possible actually. But maybe you have, and like you don't really want to track all of them, and like okay, you can do this maybe. Even that's a little bit of a stretch, because actually, yeah, I like that's just super rare. I've never had anything like that. Like if you have a 3/4 case, you generally look for beyond +1. So I don't know. I think that's it. Not sure if there's gonna be more videos. So yeah, hope you like VR.